In this video lecture, we're going to talk about chemical reactions and the resulting equations. By the end of this lecture, you should recognize evidence of chemical change, be able to represent chemical reactions using equations. Looking at an equation, you should be able to identify the reactants and the products. You're going to learn how to balance those chemical equations so that we can show matter is conserved in a chemical reaction. Chemical reactions affect you every second of every day. For example, life-sustaining chemical reactions occur continuously in your body. Other chemical reactions occur in less likely situations, such as in a thunderstorm or as in like the events that occur in this video.
Nearing the fatal end of her first Atlantic trip of the season, the Hindenburg approaches the mooring mast at Lakehurst. 21 of these sky voyages the world's biggest dirigible has made. So safely, so surely that the experimental service has become a matter of routine. Scarcely 100 feet above ground, the giant airship with her framework encasing 7 million cubic feet of inflammable gas is being carefully maneuvered towards her hangar, when suddenly... Appalling tragedy is a matter of seconds. It seems almost incredible that anyone should escape. Yet two-thirds of those on board survive what is next to the R-101 disaster, the worst in the history of aviation.
On May 6, 1937, the huge airship Hindenburg erupted into a fireball. Within a very short time, 18 seconds, the 210,000 cubic meters of hydrogen had burned and the airship was destroyed. So this is a reaction where hydrogen combines with oxygen and produced water. You're going to learn to represent this chemical reaction through chemical equations in this unit. The process by which the atoms of one or more substances are rearranged to form different substances is called a chemical reaction. A chemical reaction is just another name for a chemical change. And then, although some chemical reactions are hard to detect, many reactions provide evidence that they've occurred, such as we might see the formation of a precipitate. We might see the production of bubbles, which indicates the formation of a gas. We might smell either an odor change or the formation of an odor. We might experience the transfer of energy by observing temperature changes, so it might get warmer or it might get cooler. And we may experience that through the production of sound or light. And then finally, we might experience a chemical change through a change in color. Not like I'm coloring my fingernails, not that kind, but in a somewhat unexpected change in color. We can describe chemical reactions in several ways. I'm going to talk about 3 of them. We can describe chemical reactions through a word equation. This is a sentence that describes the chemical reaction. We could use a skeleton equation. A skeleton equation uses chemical formulas instead of words and allows us to easily identify reactants and products. We could also describe chemical reactions through the use of a chemical equation. A chemical equation adds coefficients to the skeleton equation, so it's balanced. So a big difference between the skeleton equation and the chemical equation is that the chemical equation gives us a better idea of the actual quantities of the elements involved in the reaction. The examples I've provided for each of these type of equations is the same reaction shown in all three ways. When identifying reactants and products, we've got some key words that we're looking for. And I'm going to go ahead and share that the words to form will help us to separate the reactant side of the reaction with the product side. Remember, your reactants are those substances to the left of the equation, and they are the starting substances, whereas the products are our ending substances. These are the new substances formed through that reaction. So looking at this reaction, carbon tetrahydride reacts with oxygen gas to form. So I know that the carbon tetrahydride and the oxygen gas are my reactants. Now they're forming carbon dioxide and water. So the carbon dioxide and the water are my products for that reaction. Looking at the next example, we've got hydrogen peroxide decomposes to form. So there's that to form. That tells us that everything to the right is going to be the product. So our reactant is just the hydrogen peroxide. The products then are water and oxygen gas. So we're not going to spend much time with catalysts. We just want to go ahead and make sure we define it. A catalyst is a substance that speeds up the reaction, but it's not used up in the reaction. So as the pictures show, we tend to have a quicker reaction with the catalyst. And there are a lot of enzymes in our bodies that act as catalysts for the functioning of our systems. We need to learn how to write skeleton equations because that's going to be the first step in balancing chemical equations. The first thing we need to do is write the formulas of the reactants to the left of the yield sign. That's the arrow in a reaction equation. And then we're going to write the formulas of the products to the right of the arrow. Some common symbols that we'll use are the plus sign. That's going to separate two or more reactants or products. And some verbs that we would look for in our word equation that would tell us we need to use a plus sign is added to, and, reacts with, burns in. So when you see those verbs, we're going to put a plus sign in our equation. The arrow, it's referred to as a yields sign. It separates the reactants from the products. And as I mentioned earlier, the word forms, produces, produce, decomposes to, those are all some verbs to look for to help you know that it's time to place your arrow in the equation. There are 4 symbols that help us to determine the state or identifying whether the substance is a solution, and those are also listed on this table. You would place those symbols, the SLG and the AQ, you would place those after the formula when writing the equation. And you're only going to place them if the word equation tells you specifically that, like, it's a solid substance or a gaseous substance. So if it mentions that in the word equation, then you will use those symbols when writing out the skeleton equation. All right, let's practice writing some skeleton equations. We have carbon tetrahydride reacts with, that's where we're going to place a plus, oxygen gas to form carbon dioxide and water. All right, so let's write that out. We've got carbon tetrahydride reacts with oxygen gas. Remember, oxygen is a Hofbrinkel, therefore we have to write it in its diatomic form since it's not bonded to any other elements. We also see that it is listed as a gas, so we want to go ahead and identify that it is a gas in our equation. To form, that's our arrow. Carbon dioxide and water. Okay, so the next example, iron metal. Metal tells us it's a solid, and oxygen, we're not told, we know it's a gas, but we're not told, react to produce iron 3 oxide. So I have iron, sometimes my pen doesn't work, I'm sorry. We have iron. Iron is not a Hofbrinkel, so we don't write it with a 2, but we do know that it is a solid. And oxygen. Oxygen is a Hofbrinkel. React to produce iron 3 oxide. Because that's an ionic compound, I know that iron has a 3 charge, oxygen's a 2 charge from my periodic table. So that's going to produce Fe2O3. And then for the last example that I have here, we have hydrogen peroxide decomposes to form water and oxygen gas. So we have a hydrogen peroxide, H2O2, decomposes to form water and oxygen gas. Again, because that's a Hofbrinkel, we would write it with a 2, and because we're told it's a gas, we're going to label it with a G. Our next example says we have some solid sulfur burning in oxygen gas to form sulfur dioxide. So we have sulfur, and it's a solid, burns in oxygen gas to form sulfur dioxide. And then our last example tells us we have some solid sodium bicarbonate reacting with hydrochloric acid to form aqueous sodium chloride, some water, so this is a plus, water, and carbon dioxide gas. So we have sodium bicarbonate. We're going to get that bicarbonate from the back of our periodic table with the polys. So we have some sodium bicarbonate. Both of those are 1s for their charges, so we're not going to write any numbers. But we do know that it is a solid. Oops, that's supposed to be an S. With hydrochloric acid. Remember, the hydro means I have a hydrogen, and then the chloro is going to be my Cl. And each of those had a 1, so that's why I have no numbers. And that's going to yield Sodium chloride, that's a 1 and a 1, so NaCl, and yet I have aqueous plus carbon dioxide, which is a gas. About run out of room. Now that we've practiced writing some skeleton equations, we're going to move on to the next part to get ready for balancing. Remember that the law of conservation of mass states that atoms are not created nor destroyed during a chemical reaction, but they are conserved. And a balanced chemical equation means that there's going to be the same number of atoms of each element on both sides of the equation. So the reactant elements will equal the product element number. So balanced equations then reflect the law of conservation of mass. And we can see that with our picture here. We have one black on the left, one black on the right. We have two reds on the left, two reds on the right. So it's a really good visual to show you that conservation. The steps to writing a balanced chemical equation are written here. We've learned the first step already, writing the skeleton equation for the reaction. Then we're going to count the number of atoms for each element on the reactant side, and then do the same thing for the product side. We're going to change the coefficients to make the number of atoms of each element the same on both sides of the equation. Now we cannot change the subscript in the chemical formula, because if we did that, it would actually change the identity of the substance. So H2O, if we made it H3O, would no longer be water. And then finally, we would write the coefficients in their lowest possible ratio. So we might have to reduce the coefficients if necessary. Here's a really good visual showing you each of those steps for balancing chemical equations. I went ahead and listed out some tips to consider when balancing. It might save you a little bit of time, but take one element at a time. Tackle those polyatomic ions first, because we're going to learn every time we put a coefficient in front of a polyatomic ion to change one element, it actually changes the number for every element in that polyatomic. So it's better to go ahead and tackle those first. If you have an odd number of an element, like a 3 on one side, but you have an even number on the other, realize we cannot make an even number odd, so we need to go ahead and change that odd number and make it even. And the easiest way to do that is to multiply it by 2. Realize we might have to change that coefficient later, and that's okay, but it gives us more manageable numbers and gets us on that right track faster. Something to watch out for is those diatomic elements, the Hofbrinkel twins. They're often, but not always, gases. And then remember, air is a mixture of primarily two gases, oxygen and nitrogen, but oxygen is the one that's most likely to participate in a reaction. And finally, watch out for your compounds. When you have an ionic compound, so one that includes a metal, you need to exchange those numbers. Remember, you gotta balance out the charges. And then the molecular compounds, those covalent compounds, are the ones that have the prefixes. And finally, just don't give up. Keep going back and forth, taking it one element at a time. Eventually, you're going to get the same number of atoms for each element on both sides of the equation. And at that time, if you need to reduce those numbers, you can do it then. All right, in my first example, I have hydrogen gas reacts with oxygen gas to form water, the reaction releases enough energy to launch a rocket. All right, so I know I'm going to be balancing, so I'm going to go ahead and give myself a place to write the coefficients when I get to that step. But I have hydrogen gas reacts with oxygen gas to form water. Okay? Now the easiest way to balance as we get started is to identify each of the elements and write them down in the same order on both sides of the equation. So I have H's and O's. So on both sides of the equation, this is like a division line. I'm going to write the H and the O in the same order. And now I'm going to count how many atoms I have of each of those elements. So I have 2 hydrogens over here and 2 oxygens. And then on the right, I have 2 hydrogens and 1 oxygen. All right, so now I'm ready to start balancing. My H's are the same, but my O's are not. So my O's are what's causing this equation to be unbalanced. I cannot decrease a number, so I have to work on the side I need to increase. So I'm going to go over here to the product side, and I need my oxygen to be a 2. So I find my oxygen, and in front of that formula, I write the 2. And then that gives me 2 oxygens. But you guys, when I did that, it also caused my H's to become 4 because the 2 times the 2 gives me 4. So I'm still not balanced. So I come over to the left side and I ask myself what number times that will give me the 4 that I need, and it would be a 2. So 2 times 2 is 4. So now my equation is balanced and I fill in any remaining spots with a 1. In my next example, I have hydrogen gas reacting with sulfur to produce hydrosulfuric acid. All right. Again, because I'm balancing, I'm going to give myself a place to write my coefficients. I have hydrogen gas. It's a Hofbrinkel. So it's that, plus I've identified it's a gas reacting with sulfur. Sulfur is not a Hofbrinkel, to produce hydrosulfuric acid. Now remember, hydro means it's an H, and that H has a 1 plus. Sulfuric, so sulfur, that's supposed to be an S with a 2 minus. So I'm going to exchange those numbers for my formula. So I have H2S. So now that I have my skeleton equation wrote out, I can start balancing. Again, I'm just going to list each of those elements in the same order. If you need to, separate those 2 sides. So for H, I have 2, and I have 1 sulfur, 2, and 1. So this one is already balanced. So all I have to do is fill in my 1s. Now you guys, conventionally, there are not going to be 1s there. It's just easier for us, as we're learning how to balance them, to place them as a placeholder. I have iron 3 chloride reacting with calcium hydroxide to form iron 3 hydroxide and calcium chloride. Okay, this is a 3, that's a 1, that's a 2 and a 1, that's a 3 and a 1, and a 2 and a 1. All I did was write the numbers associated with their charges to help make writing the skeleton equation a little faster. All right, so to write that out, I've got iron 1 calcium 1 hydroxide 2 iron 1 2 hydroxide 3 plus calcium chloride 2. All right, I hope I have enough room. We're going to, I like to list out the elements if you have an easier way. And I'm going to list them out in order to make verifying their balance easier. So I have 1, 3, 1. Because my subscript is outside of the brackets, it affects both elements inside the brackets. So I have 2 and 2. And then on the right, I have 1. I wish my pen would work sometimes, sorry. 2, 1. And then again, that subscript being outside the brackets gives me 3 and 3. All right, I'm ready to balance. Fe's good. Chlorine. Look, I have a 3 and a 2. Remember how I said we can never make an even number odd? So let's go ahead and get rid of the odd number by making it even. So find your chlorines and put a 2 there. That changes your Fe and it changes your chlorines. But we got rid of that odd. So then we look at the Cl. We have 6 on the left. We need 6 on the right. So find your chlorines. Give that a 3 to make your chlorines 6. But also remember that changes your calcium. So now we're looking at iron also is not balanced anymore. So let's check the iron out. But that changed your O and your H. So now I have 6 O's and 6 H's because the 3 times 2 for the coefficient gives me 6. All right, so go back to the top. 2, 6, 6. Calcium. Calcium on the left needs 3. When I do that, that changes my O's and H's. But I've got this 2 here, so 2 times the 3 gives me 6 and 6. So now I am balanced. Uh-oh. All right, aluminum is a good choice for outdoor furniture because it reacts with oxygen gas in the air to form a thin protective coat of aluminum oxide. Okay, so I have aluminum. It is not a Hofbrinkel, so I just keep it 1 plus oxygen gas, which is a Hofbrinkel and a gas, going to aluminum oxide. So my aluminum, I have a 3, oxygen, I have a 2, so it'd be Al2O3. Now I'm ready to balance. So I've got Al and O, Al and O. There's 1, 2, 2, 3. I see that I have a 3 and a 2. I don't like 3s, so I go ahead and change that first thing. That also changes my aluminum. So I go back to my aluminum, and I need a 4 here. So I got my aluminum's balanced, but my oxygens, I need 6. 2 times 3 will give me that 6 I need. They will start getting a little easier. You'll have some that are very easy. You'll have some more challenging. Just stick with them. I have calcium hydroxide reacting with sulfuric acid to form calcium sulfate and water. So I'm going to scoot over here a little bit because this is a longer one. Calcium is a 2, hydroxide's a 1. So CaOH2 reacting with sulfuric acid. So I've got the ick, which means I'm looking for the 8 poly. The 8 poly. And remember, I also am starting with an H1 plus because I am an acid. So I find sulfate and see that sulfate is a 2 negative. So I'm going to have H2SO4. Okay, looking at the product side. 2, same number means no number. So I got CaSO4 plus water. Okay, ready to start balancing. I've got some CAs, O's, H's, some more H's. I'm going to list them once because I need to know the total for the element on each side of the equation. So I don't want to separate them when I count them. And then I have some S's and then some more O's. All right, so I'm going to list those same order over here. And now I'm ready to count. I've got 1 calcium. Oops, I started to say 2, but I actually have more than that. Okay, I tried to get my eraser. Let me go back to my pen. I have the O's here. Oh, it's still on eraser. I'm sorry. Let's go back to here now. See if that works this time. I have the O's here, and I have the O's here. So I'm going to have to determine what each O is and then add them together for the total. So on this one here, I've got 2, and then over here, I've got 4. So 2 plus 4 is 6. And I'm going to do the same thing with the H's. I've got 2 and 2, so I have 4. And then finally, sulfur, I have 1. And then look at the other side. I've got 1 of those. I've got 4 O's here and then 1 here, so that's going to be a total of 5. Hydrogens, I have 2, and then 1 sulfur. So my calcium's good, my O's are not, my H's are not. I'm going to go ahead and get rid of that odd O because I have 5. So if something is making it odd, and I don't like odds and evens, and it's this one that I've underlined here that is causing it to be odd. So that's the one I need to make even. So I'm going to put a 2 there. That changes my H's. And, oops, not the S's. I still just have 1 S. It changes my O's. So now I'm going to have 6. Oh, and that's all I needed to do to balance the equation. So I'm just going to fill in the rest with 1's. And that one is done. This is the last example I'll provide for you in this lecture video. We've got dicarbon dihydride. It burns in the air. Since we know it's in the air, we know that that's going to be a gas to produce carbon dioxide and water. Okay? So, dicarbon, that's carbon 2, dihydride H2. Burns in oxygen, which is a gas, to produce carbon dioxide and water. All right, list out all my elements, C's, H's, and O's, put them in the same order, count them. That's a 2, and a 2, and a 2, and a 1, and a 2, and a 3, because I've got some here and some here. Guys, I don't like that 3 because I have an even number on the reactant side. So I find the odd one. This is the one making it odd. So I'm going to place a 2 here. That changes the H to 4. And it changes my O's to 4 as well. All right, I'm going to go ahead and look at my H's. On the left, I need 4. So I find my H's. And if I put a 2 here, that will give me the 4 I need. But that also changed my carbons. Now I have 4 carbons. So I go back over to the right side, and I know I need 4 carbons. So I place a 4 here to give me 4 carbons. And that changes my O's again. Now I'm going to have 8 plus 2. So I'm going to have 10. So all that's left to balance is those oxygens on the left. I need a total of 10, and if I put a 5 here, that gives me 10. All right, just to check that you are understanding what we needed to learn in this section of notes, I want you to go ahead and answer these 4 questions on a piece of paper, and then turn that in to me. Once you turn that in, I will give you the assignment. Thank you, and I sure hope that answered all of your questions and that you now can successfully write skeleton equations and balance them.